Hello everyone, we are back and we are going to now get into some problems where we can basically solve our confidence intervals with our z-tables. And with Mathematica to confirm that we basically have those two types of solutions available to us. So, what is the area under the standard normal distribution curve between these particular z values? So, when you look at, sometimes it's very helpful to draw these kind of distributions. So we have some distribution here. We know if we're plotting it as basically values of z, this will be centered around z equals 0. Why? Because z, remember, is equal to x minus mu over sigma. So a z value of 0 will be where x is equal to each other. So that's basically where our mean is. So we're asked between 1.43 and minus 1.43. There are two ways we can do this. We can go to our z-table. We can look at our value of 1.4 and then 3. So 0.4236. So we can do, let's shrink this little guy over here. Fantastic. So we can do 0.42, where is it? 0.236 times 2. So this would be our percentage of our data. We can also solve this, or actually just integrate this as well to confirm. So integrate PDF from z of minus 1.43 to 1.43. And again, approximately close enough, effectively the same. So you can do these one of two ways. So, fantastic. What about, let's go to the next question. Here we're asked, what percent of the population lies within the range? We know that's, well, it's the percentage, right? So 84.72% or 84.7%. What range of z will contain 90% of the data? So again, we can calculate that here. So the z value that gives us 90% would be the 0.45. So again, it'd be about 1.645. And we can solve for that. So if we need 90%, 0.90, 1.644, rounded 45. Fantastic. So let's go over here. Excellent. We nailed that question as well. Let's go to this expression. So we measured the velocity of E. coli 135 times, so large sample size. Velocity was determined, the mean, so and we're going to assume that this is approximately our population, was 3. Our standard deviation was 0.1. I'm interested in the velocity measurements between this value and this value, and the percent that fall within that range. And I'm planning to claim that 90% of the data will fall in this range. So what assumptions are you making about the data? Normally distributed, large sample size. Z value, because if we're going to calculate the measurements that fall between those two values. So my Z1 value is equal to, let's go ahead and pull this down. Z1 value is 2.857. I'm going to call this my mu for this problem is equal to 3. My standard deviation for this problem is equal to 0.1. And our Z2 is equal to 3.143. So, actually, I'm going to call this not Z1. I'm going to call this X measurand 1, measurand 2. So my Z function, which is going to be, I'm going to create a function. I'm going to plug in an X given a mu, given a standard deviation. And I'm going to set this equal to X minus mu, all of this divided by SD, standard deviation. Excellent. So I can now just plug in Z function of what's my X1, and my mu1 and my SD1, and I can z function of x2, mu2, actually mu1, SD1, and voila. So same answer as last time, by coincidence or by design. So we know the area 84.7. How many measurements? How many percent fall within this range? How many measurements is a good question. So let's say I were to, let's do the integration, or actually we have the integral right here. So I can now multiply this by 135. So we should expect about 114 measurements to fall within that range. And what range of, this is a very good question. What range of velocities will contain 95% of the data? So we're looking for measurands here, correct? So I can go ahead and say zfun x mu1 sd1, and we need to solve for, because we know our z value that will give us 95% is 1.96. So we need to solve when is this equal to 1.96, and we get this. And then you could also do, again, if we're looking at symmetric, minus 1.96, and you can get your range of velocities here. So that's it. Next time, we'll go through our marble diameters and ultimate tensile strength and voltage measurements and other values too. So we'll see you in the next video. Thanks. Bye.